Before we talk about the details of metadata, let's take a look at the basic structure of a video frame. What's worth noting is that the structure you see is the same structure whether it's a 720 frame, a 1080, a 4K, or even an 8K frame. The part of the video frame I'm showing here is that area that you see on your phone, on your TV, or even in the theater. When the Society of Motion Pictures and Television Engineers, referred to as SMPTE, designed the video frame, they designed spaces around the active video area to hold data that was important. One of those data points is the horizontal ancillary space. This is an area of data that's on every line. And they also should have the vertical ancillary data space in yellow here on the line. That appears in each line. Also common to every video frame is an area called the start of active video. The start of active video is a fixed data pattern that appears in every line that indicates where video will begin, except in the first few lines up here in the horizontal ancillary space, and the bottom few lines in the buffer space. The start of active video data pattern cannot appear anywhere in the video space to ensure that synchronization is accomplished on every line. The other critical point that appears in every frame is the end of active video. And in the end of active video is a fixed data pattern, also different than start of active video, that tells any decoder where the end of the line is. The important space between end of active video of the previous frame and start of active video of the new frame is the horizontal ancillary space that you see here in purple. This is a very critical space. It includes information that's used by decoders to describe the type of video format that's coming, a 1080, a 720, a 4K, its frame rate, whatever those frame rates might be, and other information about the video payload itself. Also critical to that space is the audio channels. All of the AES audio bytes appear in this horizontal space and are actually the bytes used for the subsequent frame, even though they're counted in the pixels of the previous frame. Other things in there are film codes for synchronizing from film imagery to digital imagery because of the different frame rates. There's workflow data, there's copyright protection data, there's billing information, there's parental controls, there's many other elements that are included in that data space. The vertical ancillary space, referred to as the bank, generally doesn't have very much information in it at all. Line 14 is customarily used for scene switching, so that when you go from one camera to another, or if you're splicing from one scene to another on a digital format, that happens at line 14, which is out of the viewing area in the lines that follow. Also, there is a line generally used for closed captioning in the television world, so that they can have closed captioning for hearing impaired and things of that type. Sometimes the alternative language is up there as well. In the cinema side, it might be used to capture lens settings, lighting settings, positions of actors. All of this data is generally wiped out at the time of distribution. And distribution is in the theater, on your phone, on your TV, or on a DVD or Blu-ray disc. So in this space, pixels are image data. In this space, pixels are repurposed image data as information. The most common sampling technique is 422, meaning that there is one color sample per 2 pixels. That's used to save bits in the image stream and has very little effect on your perception of what is seen in the image area. Each pixel then can carry data. It can either be image data, or in the Bank and Hank space, it's repurposed to bytes. So a 10-bit deep image sample, the first 2 bits are used as parity and not parity, and then the remaining 8 bits are bytes. All of the data carried in the Hank space and the Bank space is carried in the There are several types of packets that SMPTE has defined for the ancillary space, but the one that we're interested in is in the Bank space, and it's the key length value, KLV, type of packet. That packet is signified in the line stream with an ADF signal. That's an ancillary data flag. That signal tells the decoder that a data packet is coming and not an image packet. And then the data item description defines it as a KLV packet, and the SSID says it's a type 2 KLV packet, which is a specific structure for the Bank space. The data count says how many bytes follow, how many samples really follow. And that's this entire area called the user data word, and it's parity not and parity bit, followed by the checksum. All of those things are the elements and basic structure of a metadata packet, a KLV metadata packet. These are found in SMPTE Standard 291 for Type 2. They include those wrappers as I described. But what's really important is the user data word. This is the place where the KLV packet is defined to exist, and the content of this is what we get to use for data space. And it can be a general purpose data space, as we'll learn as we go. One of the things of note that's pertinent to our industry is the Motion Imagery Standards Board, we lovingly refer to as MISB, uses the Type 2 KLV packet, which is in fact the SMPTE structure. That SMPTE structure, as I said, is key length value. The key is an identifier for data type. It can say that this is all ASCII, this is floating point numbers, or group of floating point numbers, or group of integer values, and that's what that key will tell you in a big lookup. The lookup is a dictionary. The dictionary is a place where you'll find that number, and next to it you'll find a description of what is contained in that key length value packet. The length is the number of bytes of the value payload part of the packet, which is the value part right here. The length is 1 byte, and the key by definition is 16. Sometimes you need long messages, or you choose to have long messages, in which case you can use the message ID and the 2 program segment counters that will allow you to have a message that is comprised of many packets. And this tells you, as you go through the decode process, how to reorganize those in the proper order. The definition then is 16 bytes a key. There is 4 bytes associated with the 3 bytes associated with the message ID and the PSC, and 1 byte of length. So you have 20 bytes of the 255 that are available in the user data word are consumed by the key length value structure. The balance of the bytes, the value, can be anywhere from 1 byte to 2. And that's the key to the KLV metadata packet. It can be any data in the value space. We can have bytes that are assigned to ASCII, binary blocks, values such as integers, floating point, and so on. And the memory, the value can be treated as memory space. It's just a memory location from the first byte to the 235 byte. and anywhere in between. So you can assign a value with an offset from starting from byte 1 in the value into the memory space up to 235 bytes. So you can assign that data. And that flexibility allows us to use the KLB metadata packet for telemetry purposes. MISB bought a block of numbers from SMPTE that is a volume of the SMPTE dictionary. MISB can use these numbers, this volume, and this group in red, and this group in red, identify the numbers assigned to it by SMPTE. The numbers in between can be assigned by MISB, and that forms the MISB dictionary, which right now has about 980 keys that are registered in their standard 807. And you can find that list online as shown here to locate a key that might be of interest or use to you. Most of these were derived for UAV uses. In fact, if you take a look at the first couple of hundred keys, they were actually designed within the Predator program to take information for these initial UAV and the way they were testing them and the way they used them. Of most significance is the microsecond timestamp. That's used universally between SMPTE and MISB. It has the key shown here, and you'll note that the first digits are the digits assigned to MISB use, and the middle digits are also the digits assigned to MISB for their use. The microsecond timestamp is a standard structure that contains 8 bytes. That is the number of microseconds since January 1st, 1970, which also happens to be the Unix epoch. There is 1 byte preceding it, those 8, that is a status that identifies whether it's valid time, whether the time was taken from a locked source, locked to a standard such as GPS. And the balance of it is the key number and its length, which would be 9 in this case. So the MISB key, as shown down here, has the 16 bytes identifying these digits for the key lookup, the length of 9, as you see here, and then a structure of 1 byte of status and 8 bytes of microsecond count since January 1st, 1970. That is the KLB packet in the bank space. That is the microsecond timestamp that's used by both SMPTE and MISB, and is what's referred to in our world as the microsecond timestamp or the MISB timestamp and several other names. All of our equipment comes with the ability to write and decode the microsecond timestamp and convert it to Julian or Gregorian dates for overlay. Now here's what's going on with metadata that makes it important for testing and evaluation of the behavior of things. You can put metadata in uniquely on every frame. You can put it there, not put it there. It could be different data, it can be the same data. It doesn't really matter. But what is important here is we can sample data on every video frame and now have data that's synchronized to the image. And that will help you study the behavior of things, such as when they fall. You can see how velocity changes, you can see how they bounce, you can see how wind affects them, you can see stresses, you can take data from sensing devices and use the imagery together to see stimulus and response. There's tremendous value in using the metadata with video, and you can do this as you go with the live video stream. So each frame then can be data that is sampled relevant to that particular image. So if you see something bending, you see something moving, you see something coming apart, you see something imploding or whatever, you can actually see other data from other sensors sampled at that particular time and get a better sense of what's happening with a device or block diagram I'm showing here does use ITS equipment, but this could be done other ways as well, providing you have the right equipment. But here you can see I'm showing a video source, such as a camera, that's generating this video stream. That video stream is going into our 6520 inserted recorder in this image. And it's capturing video, or can capture video, while the video is coming in, and save it to either volatile or non-volatile memory. Concurrently, over here, we have a piece of software that can run on a PC called our Data Concentrator. What's really unique about the Data Concentrator is that you can send data to this PC from multiple sources and inform the Data Concentrator where that data is and how to parse it, and then take the most interesting pieces of data, or the relevant pieces of data you choose, and map those to a key that you've created that will put that data and populate the metadata space, those 235 bytes, if you choose to use it all, with the data that's coming in from each of these sensors asynchronously. Once it has a complete packet of information, you can tell it how frequently to send it to one of our devices. It will take that packet, package it up with some ITS commands, and send it off to our recorder. The recorder then will take that payload and encapsulate it in the KLV metadata pack along with the key number that you've assigned to this particular key structure. And as the video comes in, actually put it up on line 9 right after the MISB timestamp that it writes on every frame. So you can be sending data to us with the Data Concentrator, for example, up to 200 times a second. And if the incoming video is coming to us at 60 times a second, we'll subsample that. And what you'll have here is a frame of data, a frame of video, a frame of data that is captured from this data coming to us is the last full packet that we've received. So the staleness of this data is much less than a video frame time, which is very valuable. Now this data is very, very close to the image itself, and you can see what's going on and use that for. On the playback side, you have several choices with our recorder. One of those, you can be playing back live, and while you play back, you can tell the playback channel, capture the video, capture the metadata out of it, parse it, and actually overlay it on the imagery as it's playing back. It doesn't affect the images. This is another value of using metadata versus overlay. At the time of recording, if you only use the metadata and don't have any overlay, every pixel of the frame that you can see is clean. There's no text, there's nothing getting in the way of your observations. So something happens in a corner, you chose to put some data, which if it burned in, it's gone forever. In this particular case, whatever the camera gave you, you got. In fact, that's one of the things that we tout in our recorder, is that we're recording uncompressed video. So whatever the camera we got is the camera we record, and it's also the video that we play back, is whatever the camera gave you. The metadata then can be played back and overlaid for observation. It can also be extracted, and it can be then played back with key read, and you can see that extracted to a file, and then you can actually look at the data that was captured, all formatted the way you identified that data to be. And then that can be output to a comma-separated value file, which can be used by almost anything. So we have a tool set that will take you from start to finish. You can design a key, you can insert data, capture data and insert it into live video. You can play back that video, decode it, overlay it, record it to a file, and then convert it to a CSV file for use by MATLAB or Excel or other products that you might generally use for data analysis and charting. Thank you. I hope you found this informative.